Okay, class has officially begun. Welcome to physics. Before I start, let me remind you that the way I take roll is for you to type something into the chat box. I see most of you have done that, but a few of you haven't. You don't get credit for being here if you don't say hi in the chat box or something similar. All right, how about questions from last night's homework? Or questions about anything in general? Not hearing anything? Not seeing anything in the chat box. Does that mean last night's homework was really easy? If so, I can always make it more challenging. Tonight's homework, I think, will be good. I think you'll enjoy it. Maybe a little more challenging, but I don't think it's too hard. Please, no. Yeah, the last problem was really hard. Well, okay. I agree that the last problem was hard. That's why we did it together. I didn't expect you to do that one on your own. If you followed through what we did in class, we did that one together. Now, later on in the year, I am going to expect you guys to be able to do stuff like that on your own. But for right now, yeah, we start off a little bit easy. Okay, so Jonas, I see you had a question on number 10. Do you have a specific question you wanna ask? Not seeing or hearing anything. Tell you what, Jonas, if you want to, or anybody, if you want to hang around after our online class is over and after everybody else has logged off and said goodbye, if you want to do some one-on-one chatting, I am absolutely available to do that. Okay, let's talk about the answers that you gave to the homework last time. Let me pull it up so that it'll make it a little easier for us to talk to. Hopefully you guys can see my Canvas screen right now. And let's scroll down to the assignments. Now remember, my page looks a little different than yours does. All right, so the Flat Earth assignment part 1 is the one that was due today. Notice I did post a video of the class where we basically went over all the answers. The only one that we didn't do together was the one where you had to calculate the mathematical model for the round Earth theory, because basically we had the 2 points and all you had to do was come up with the equation of the line given 2 points. That's something I trust you could do. A couple new things that appear down here we're going to talk about later, especially this $5,000 Flat Earth Challenge. We're going to talk about that in just a few minutes. But first, let's go into the Flat Earth assignment part 1. And let's talk about the first problem. If I click on preview here, it'll look a little bit more like it does for you guys. Okay, so as I'm sure you remember, the idea was we were going to try and prove George Bernard Shaw to be wrong, where George Bernard Shaw said that the average man, let's see, so the average man or woman can advance not a single reason for thinking the Earth is round. They just swallow this idea because it sounds good. All right, so we're going to try and prove him wrong. So you were supposed to list as many reasons as you could, or at least one, for why we should believe that the Earth is round rather than flat. Now, some of your answers were really good. A few of your answers were ones where me and my friends at Flat Earth Society would not be able to argue against you. Remember that $5,000 challenge that I talked about? That was something that one of the founding members of the Flat Earth Society, he put up a $5,000 challenge saying, if you can prove that the Earth is not flat and absolutely prove it rigorously, he'll give you $5,000. And that was back in, that was about 90 years ago. And so if you adjust for inflation, that $5,000 then is the equivalent of about $85,000 now. So this was a big prize. And some of you would have won that prize because some of the arguments that you submitted were really good, solid ones that me and my friends at Flat Earth Society would not be able to argue against. Most of the ones that you answered were ones that we can't argue against, and we are going to talk about those in a minute. A few of you did not follow the instructions that I gave you. I specifically said that you can only include observations or measurements that you yourself could personally do, and I also said that you have to do it without leaving the state of Utah. So several of you included arguments that required you to leave the state of Utah, which was specifically prohibited. Okay, so I'm not going to take the time to argue against your arguments. I don't want to take the time to do that, but I am going to refer you to this really cool article that I've posted here. This is the $5,000 challenge article. Okay, so it was published in a magazine about 90 years ago, and let me make it a little bit bigger here. So one of the founding members of the Flat Earth Society said that he would pay $5,000 to anybody who could prove that the Earth was not flat. And as I said a minute ago, some of you would have won that challenge. You did a really good job. Most of you, however, now the arguments that you posted actually are correct, many of you. But they're ones that me and my friends of the Flat Earth Society could successfully argue against, okay? Like for instance, some of you said, well, if the Earth was flat, then the sun would never rise or set, which actually is technically correct. But my friends and I at the Flat Earth Society, we have an argument against that. I mean, I'm not claiming it's a great argument, okay? But it's an argument. Okay, so let me talk about what we believe, wink, that the Earth looks like. Okay, so the Flat Earth Society believes that the Earth is a round disk, and the sun is up here. Let me turn on annotation here so I can highlight things. So the sun is not really 93 million miles away. It's kind of like Polaris. It's only about 3,000 miles away. And it's on a disk that rotates every 24 hours. And so what you see here, the sun is now over Australia. So for the people over here in South America, the sun is so far away that the light can't make it through all that haze, and therefore it gets dark. So I'm not claiming that this is a fantastic argument, but it's one that we use. So Lila has a really good question. Wouldn't it kill us if that was that close? And the answer to that is, well, if the sun was as powerful as scientists claim that it is, then yeah, it would kill us. But me and my friends of the Flat Earth Society, we say, well, the sun's not really that powerful. Okay. Okay, hang on just 1 second here. Somebody just joined the class. I need to mark them tardy. Okay. All right. Okay. And so Teague is asking about, is the Earth is balanced on 4 elephants or a cosmic turtle? And yeah, you are correct. That's what we believe. Wink. Okay. Now I don't want to spend too much time on this, but I do highly recommend that you guys read this article. It's a good article. Talks about a lot of important things. Now this here, this is one that some of you mentioned. Let me see if I can make, no, I guess it won't let me make it bigger. Okay, here we go, make it bigger here. This is an argument that some of you mentioned where you violated the rules that I gave you. Remember how I said that you're not allowed to leave the state of Utah, but some of you said, well, what if you were to get in a boat and sail around the world? Which, by the way, I have done. And so people will say, well, if you've sailed around the world, then how could you possibly claim the Earth is flat if you've sailed around it? Well, actually, my friends at the Flat Earth Society and I, we actually have an answer for that. We claim, wink. Now remember, if you're taking notes, note that I'm winking while I say this. We claim that the North Pole is in the center of this disk, and there's a great big magnet buried at the North Pole. So when you get in a ship and you head east, actually what I did was I headed west. I sailed off into the sunset, but it doesn't matter. It doesn't matter what direction you go. So in the drawing here, it shows it going east. So let's say it's east. All right. So you sail east. How do you know that you're traveling east? Well, because you're looking at your compass. but the compass always points to the magnetic North Pole, which is in the middle there. And so when you get over to this part right here, okay, your compass points that way. And when you get over this point right here, your compass points that way, and so forth and so on, okay? So you don't realize it, but you're actually turning ever so slowly. And so it's no surprise that you end up back where you started from, okay? So that's the flat Earth argument against that. All right, so Carrie is asking, where do we think the South Pole is? All right, so there's another good drawing here for that. Let me get this up here. Okay, well, let me go back up to this original one here. So you see around the edge here, let me turn on annotation. Okay, so see the edge here? That color doesn't show up great. Let's try red, okay? We in the Flat Earth Society, we don't believe that there really is a South Pole. We believe that if you keep going south, you're eventually going to get to an ice wall, which people call Antarctica, but it's actually a great big wall. It's not really a pole. And again, let me say wink while I say this, okay? Now, I don't want to spend a whole lot of time talking about this article, but I do highly recommend that you read it. Okay, I'll accept one more question. So Teague is asking, how does the flat Earth have seasons? We've thought about that. We have some really well thought out arguments. I'm not saying that they're completely valid, but they are well thought out. Okay, so take a look at this drawing right here. Okay, so remember, Teague's asking the question, if the Earth is flat, how can it possibly have seasons? All right, well, we believe, wink, wink, that the Earth is up here, and, or I'm sorry, that the sun is up above the Earth here, but the sun is tied on a rope, and there's pulleys on the rope, okay? And there's somebody, maybe it's an angel, maybe it's who knows, but somebody's job it is to pull this rope, and they pull it really slowly. So the sun moves north and south depending on what season it is. So in December, the sun is really far south. Okay, and then as the months goes on, this angel or whoever it is whose job it is to do this, they're pulling on the rope, and the sun moves slowly northward, and so then in June, the sun is as far north as it ever gets, and then it turns around and goes back the other way. Okay, so like I say, I'm not claiming that these are great arguments, but they, they're fun to play with, and conceivably might be true. So the arguments that you guys suggested in your homework last night, some of them were really good arguments that you would have won the $5,000 challenge if you had submitted them back 90 years ago. Others of your arguments are good arguments, but me and my friends at Flat Earth Society have counter arguments that kind of sort of work against them. So let's not talk anymore about these other arguments. Let's focus on the one method that we have agreed we're going to use in this class. And that's the idea where we're going to do this experiment where we start off at the North Pole, we measure the angle of Polaris, and we keep moving south and keep measuring the angle of Polaris as we move south, okay? And then we create our two mathematical models. The one mathematical model is the one that fits the round Earth hypothesis. The other mathematical model is the one that fits the flat Earth hypothesis. And we're going to come up with the equations. In fact, we did. Last time we met, we did come up with the equations for these mathematical models. So what we're going to do today is we are going to compare the actual measured data with our mathematical models. And we're going to see whether or not that can disprove the flat Earth hypothesis, and whether or not it can prove the round Earth hypothesis. All right, so let me share my screen here. All right, so let's get out of here. Okay, so let's go back here into our modules. All right. So let me just recommend again that this Flat Earth Challenge, I highly recommend you download it and read it. It's a lot of fun, and it's some of the arguments there they're certainly worth thinking about. Okay, but our homework for tonight is the flat earth assignment part 2. All right, so let's click on that and see what we got. All right, and let me click on preview so that my screen looks a little bit more like what your screen will look like when you click on it. All right, so here is just a reminder of what we did last time. This equation right here was what we called the round earth mathematical model. So it is the equation that fits the data that we would get if the earth is round. And if the independent variable in our experiment is our distance from the North Pole, so that's the x, that's our distance from the North Pole. And then the y is the angle of Polaris above the ground. So if it is true that the earth is round, the data would have to fit this model. On the other hand, if the earth really is flat, then the data would have to fit this model, where again, the x here is the distance from the North Pole, and the y here is the angle of Polaris above the horizon. All right, so these are the mathematical models, and we're going to see if the data fits the model. Okay, and let's just remind ourselves about how we measure these, because there's some really important things that are going to come up on this. So the easy way to measure the angle of Polaris as we walk south from the North Pole is with this protractor here. We've got the straw taped to the top. We've got a weighted string hanging down, and we just look at Polaris through the straw, and then we see how many degrees is it from the straight down position over to where the string is. Just count those degrees. All right, that will tell us the angle of Polaris. But how much precision will that give us? You guys remember when we talked about that? Somebody either type into the chat box or unmute yourself. What is the level of precision that we can get if we use this tool here? Can we get a precision of 1/100th of a degree using a protractor?
You can't get it down to 1/100th of a degree.
Not even close.
Not accurate.
Yeah.
It's good for getting like a general.
Yeah. So we said that maybe if we're lucky, we can get plus or minus 1 degree using a protractor. And to be honest, even that's kind of pushing it. Probably more likely is plus or minus 2 degrees. But if you're super careful, in theory, yeah, maybe you could get a precision of plus or minus 1 degree. So what did we do then in order to get a precision of 1/100th of a degree? Because remember, when we came up with our mathematical model, we said that when we measured it from Salt Lake City, when we measured the angle of Polaris, I said that it was 40.75. So I claimed that I knew that number with a precision of 1/100th of a degree. What tool did we use to do that? Come on, somebody needs to speak up here. What was the name of the tool that can give it that kind of accuracy?
Protractor?
A sextant?
A sextant, yeah, not a protractor. The protractor, the best we can hope for is plus or minus 1 degree of precision. But a sextant, that can give us plus or minus 1/100th of a degree, all right? Okay, now keep that in mind as we do this experiment, or as we go through what we're going to go through now. Let me go back to share my screen again. Okay, so keep that in mind here. Now, what you see on your screen right now is actual data that has been measured. And you remember the rule that I had here was you weren't allowed to leave the state of Utah, right? So, so here is data that was taken from within the state of Utah. And so the numbers you see right here, these are the distances of the various cities from the North Pole. So Logan is 3,333 miles away from the North Pole. That's a number that's pretty easy to remember. Salt Lake is 3,401. St. George is 3,654. All right. So we know the distance from the North Pole. So that is going to be our X value. That's going to be our independent variable. And then if we used a protractor to measure the angle, then these are the numbers that we're going to get. And so let's call this Y. So we got our X and we got our Y. And now you'll notice that I also have numbers if you use a protractor. So how about let's call the Polaris angle measured by protractor, we're going to call that Y1. And the Polaris measured by a sextant, we're going to call that Y2. So this is the measured data. And our job today is to compare this data with the mathematical models that we developed last time. And we'll see how well the data fits the model and see if that would allow us to conclude with confidence that the Earth is not flat. And we'll see if it allows us to say that we have proven that the Earth is round. All right. Now, what we could do is we could go into Desmos. In fact, what we're going to do is go into Desmos, and we're going to use Desmos to plot this data for us. And because I'm such an incredibly nice guy, I have actually done it for you. When you go into Canvas and you click on this assignment, it'll take you to this link right here. If you click on this link, look what happens. It opens up a Desmos page that I have created for you. And there it is. The data is already there. So let me turn on annotation here. All right, so these numbers are the distances for the various cities. 3,333, so that corresponds to Logan. 3,401, that corresponds to Salt Lake City, and so forth and so on. Let's see, that last one. I've got some windows in the way here that you guys don't have. Let me see if I can minimize those windows. Okay. All right, so that takes you to St. George. All right. And so what you see right now is you'll see that I've got this little icon right next to the Y1. I have clicked on that. So that is the one that is currently active. If I click on the other one, okay, and so now you see this is the sextant data. And let's go back to the original one. So the numbers that you're seeing there, that's the protractor data. All right. And the curve that you see right here, or the line that you're seeing right there, let me, I didn't mean to do that. Let me refresh here. And let me turn off annotations. All right. All right. So the curve, the equation there that you're seeing, that is this equation right here, because you see that's the one that's highlighted, right? Which equation is that? Is that the round Earth model or is that the flat Earth model? Somebody speak up here.
The round Earth model.
Okay, that's the flat Earth model. Yeah, the inverse tangent one is the flat Earth model. All right. Okay, so now what I could do is I could turn off the flat Earth model. So I click on that and the flat Earth model goes away. Underneath it is the equation that's the round Earth model. Okay, and in fact, I can turn both of them on. All right, so I've got both models turned on. And tell you what, before I go on too much further, let's make sure that we agree that these models fit the way that they're supposed to. Let me zoom out. Remember, one of your homework assignments was to come up with the various models. Oops, so if I move my mouse without clicking first, it does that. All right, let's just turn on this model right here. Do you guys agree? Does that match what the round Earth model is supposed to look like? It's a straight line. And it has one point right here, which is 0, 90, has the other point down here, which is 62, 15, 0. So I'm thinking, yep, this equation right here is in fact the round Earth model. Okay, so let's turn that off and let's turn the other equation on. All right, does that equation look like the flat Earth model is supposed to look? Again, it starts with 0, 90, just like the round one does, but you'll see that it is asymptotic. In fact, I can even zoom out a little bit more here. If I zoom out a little bit more, you see, okay, clearly it's asymptotic to the y-axis. Now, there is one thing I need to warn you guys about, radians and degrees. I'm sure that some of you have heard about radians and degrees. If you were to create your own graph of this data up here, what you're going to find is the graph doesn't look like that because the default mode for Desmos is not degrees. The default mode is radians, right? So when you graph it, if you don't change it from degrees to radians, your graph is going to look like this. You see there is a line, it's way in the world down there. Okay, so when you graph the data, you're going to say, wait a minute, something's seriously wrong. The round earth model right here, yeah, round earth model looks great, but the flat earth model, there's something seriously wrong with the flat earth model. Well, it's just because the default mode for Desmos is radians. So you got to be careful about that. You got to click it in degrees and then everything will be fine. All right. So hopefully you guys now agree that the two equations we've got here actually do model what we want. So let's come back in here and let's zoom in on just the data from Salt Lake City. All right. Let me ask the question. In fact, tell you what I'm going to do here. I'm going to take a poll here. And so I'm going to make a statement and I want you guys to tell me whether or not you agree with the statement that I make. So the statement that I'm going to make is, do you agree that this data proves that the Earth is not flat? Right? So you should see a poll on your screen right now. Do you agree that this data proves that the Earth is not flat?
Are you saying the data of the sextant or the protractor?
Well, the data that you see on the screen right now is the protractor data, not the sextant data, all right? So if we look only at the protractor data, which is the data that you see on the screen, and you can see it doesn't fit the line very well. You know, these guys right here are below the line. This one here is above the line. So it doesn't fit it perfectly, but it kind of sort of fits it. So the statement is that, you know, somebody says they think this proves that the Earth is not flat. Do you agree or disagree? I still need 4 more people to chime in here. 3 more people now. Everybody has to vote here. Now, I don't see who said what, so don't worry that don't worry about being embarrassed if you don't know the answer. Okay, 1 more person still needs to answer. Come on. All right, maybe that 1 person fell asleep. All right, I'll go ahead and end the polling here. All right, so 15 of you said that you agreed that this data proves that the Earth is not flat. 8 of you, however, said that you did not agree. If you are one of the 8 people who said that you do not agree, can you please unmute yourself and tell me why did you disagree with this?
So the data from the protractor, it's not precise enough. It doesn't fit the line well enough. And maybe we can see the flat Earth line too.
Well, what you're looking at is the flat Earth line.
Oh, that is?
Yeah, this is the flat Earth line.
Oh. Because that it also fits the data just as well as the round Earth at this point.
Well, it fits it pretty well. I'll go ahead and turn it on. Okay, there. All right, so the red line that you see is the flat Earth data. The blue line is the round Earth data. Which one fits better?
I would say the round Earth probably, but they both kind of look.
Yeah, they both kind of look okay. Right. So somebody else who said you disagree. Tell me, why did you disagree?
Well,
prove is
okay.
Strong. Yeah, prove is a very strong word.
Proof is a very strong word.
You the way that we calculated this one was by fixing it to the Salt Lake City point, 0.90. Like you use that to calculate your graph. So I think we needed to spread it out a bit more. For at least for the flat Earth one, like pick a different point on the Earth's surface to find it, and then compare it with the different ones around Utah.
All right. Okay. I like what you're saying. Now I heard somebody else trying to say something too. It was a female voice.
Yeah, that was me. I was just saying that I picked no because the data doesn't really match up very well. It's all kind of over the place. It's not like when you showed us the Sexton data, that it was very accurate, so you could see it very well. And I would say this would be more of highly educated, like not theory, but like it's not quite proof. Like it's almost there.
Okay. All right. I like very much what Lila is saying here. She's really got it nailed. Lila says that the data that we're looking at is data that was obtained with the protractor. And remember, we said that when we measure stuff with the protractor, the best we can hope for is a precision of plus or minus 1 degree. So there's a substantial amount of uncertainty in our protractor data. That's the key thing, uncertainty. So keep that in mind. All right, so what I'm going to do right now is I'm going to turn on what are called error bars. And this is something that I understand from your math teachers. Your math teachers don't ask you to do when you plot stuff. But see, in physics, we have to recognize that whenever we look at measured data, there's always some uncertainty in the results there. So if we come down here, I've plotted a really neat thing here that your math teacher probably hasn't told you how to do in Desmos. You see this equation right here? This is a way where we can plot what are called error bars that will allow us to measure how much certainty there is. So I'm going to click on this thing right now to enable that. You see those bars that just appeared? Those bars are plus or minus 1 degree from the measured data. All right, so when we measured the data in Logan, we thought that this right here is what the data was. But in fact, because of the uncertainty with this silly protractor that we're using, the real answer could have been anywhere in that range. And same thing, here in Moab. The real answer could actually be anywhere in that range right there. So if we don't include error bars in our graph, then we cannot say with certainty whether or not our data means anything. So let me do this. Let's suppose that we didn't take data in Cedar City or St. George. Let's suppose that the only data we have is data from Logan to Moab. So if we ignore these guys right here, now let me ask the question again. Now that we can see what the uncertainty level is in our measurement, okay, I'm going to take the poll a second time. Now, can we say with certainty that this data proves that the Earth is not flat? Okay, about half of you have responded. Interesting, it's close to half and half so far. I need 3 more people to respond. 2 more people to respond. Come on, 2 more people. All right, tell you what, I'm not going to wait for the 2. All right, let's look at the results here. All right, so it's pretty much split half and half. All right, and again, what I'm going to say of someone who has not yet spoken, who is in the group that said that you disagree. So what you're saying is you disagree with the claim that this data proves that the Earth is not flat. Somebody speak up. Tell me, why do you say that? Nobody wants to speak up? Okay. All right, well, I'll tell you why I disagree with it. All right. If you look at, in fact, let me close this window here because it's kind of blocking my view here. All right. if all you're looking at is this data, you see the line here, which is our mathematical model, it passes through each one of those groupings. Okay. Now, admittedly, down here in Moab, it passes through the upper part of the grouping, and down here up here in Logan, it passes through the lower part of the grouping, but it passes through there. Every single one of those groups, okay, that line passes through it. And so because of the uncertainty, we cannot say, based on this data right here, we cannot say with certainty that we have proven that the Earth is not flat, because the line passes through the data points. But if we include all of the data, so now let's say we go down to St. George. Take a look at St. George. You see, this is the number that we measured, and we are certain that the real answer is somewhere in this range here. Now, it might be clear up here, it might be clear down here, but we are certain it's somewhere in that range. Now, if the Earth really was flat, we got a problem here, because this data point that I just made a big circle of, that data point falls outside of the area of uncertainty. We can say with 100% certainty that we are sure now, because of the St. George data point, the St. George data point falls outside of the model, and even with the error bars, even all of the error bars, they are outside of the model. So we can in fact say with certainty that the Earth is not flat, but we have to drive all the way to St. George to do it if we're going to use the protractor. Okay. Now, if we stopped in Cedar City, then things get really interesting. So let's suppose we didn't go to St. George, but we stopped in Cedar City. We would have a problem right there. Okay, that the model passes just barely through the edge of our uncertainty region. So if we stop in Cedar City, we cannot say with absolute certainty that the Earth is not flat. But if we go all the way to St. George, okay, yes, that's it. That St. George data point, that's the one that proves without a shadow of doubt the Earth is not flat. Okay, so we have just won the $5,000 challenge here, and we did it without leaving the state of Utah. But we did have to drive all the way down to St. George. All right, so in your homework tonight, you're going to have to basically recreate that. And then one of the questions in the homework is going to be, well, what if we use the sextant instead of the protractor? All right, so remember, this data right here, this was all the protractor data. Our sextant data is this data over here. All right, so let's click on this here to get rid of the protractor data. And by the way, let's get rid of the error bars as well. Those error bars go with the protractor data. Now I'm going to click here to turn on the sextant data. Aha, sextant data looks much more interesting here. All right. So if we look at the sextant data, then we say, okay, we've got a whole bunch of data points. All of these data points are below the line. These data points are above the line, maybe not very much, but they're above it. Okay, so it's looking more certain that we could say that we've proven that the Earth is not flat, but we haven't got our error bars yet. Remember, we got to turn on the error bars. Okay, so if we come up here, this expression right here, this is where we do plus or minus 1/100th of a degree. Okay, so if I click on this icon right there, that will turn on my error bars. So there we go. I've turned on the error bars. Now I don't notice much different there. In fact, tell you what, let's toggle it on and off. I toggle it on and off. I don't see any difference, right? But if we zoom in, okay, there. Okay, there's a data point. So, oops, I hate it when that happens. Okay, I got to remember to click the mouse before I move the mouse. Okay, so I'm going to turn the error bars off. Now I'm going to turn the error bars back on. Okay, so the error bars are in fact on. It's just that when we zoom out here, those error bars are so incredibly small, we can't see them, but they are in fact there. All right, so if we use the sextant data, then we have a much more accurate result. And so now you can see that we don't even need to drive all the way to St. George. Let's just focus in on this data here. Oh, and again, I keep moving my mouse without clicking it first. Okay, let's just look at from Ogden to Salt Lake City. Okay, the Ogden data point, remember there are error bars in there. You can't see the error bars up there, but they're there. The Ogden data point lies outside of our model, even with the error bars, as in fact, so does the Provo model. So if we're going to use a sextant, okay, if we are lucky enough to have a sextant, we can take a measurement point in Salt Lake City, drive down to Provo, take another measurement point, and we're done. Because of the incredible accuracy of a sextant, we don't need to drive all the way to St. George. Okay? Just from Salt Lake to Provo, that's all we need, or Salt Lake to Ogden, whichever way you want to go. Okay, that's enough to say that we have in fact proven that the Earth is not flat. Okay. Are there any questions about that?
I don't think so. Oh, and how are you going to grade us on that quiz?
On last night's quiz or on tonight's quiz?
The one that I had trouble getting into.
Well, I mean, last night's quiz, we basically did the quiz together in class last time. There was only one question that we didn't do together, and that was finding the equation of the flat Earth model. But of the rest of them, we all did together. So if you didn't explain it right, then I'm not going to give you credit. And then tonight's model is basically kind of to recreate what we're doing right now.
Hang on, right. 1 second.
So if you have a more detailed question, how about stay online after everybody else logs off once you and I talk privately.
Okay.
So it looks to me like we have now proven that the Earth is not flat, which is really a bummer for me because I just got through sending in a check to renew my membership in the Flat Earth Society. Rats. Well, doggone. Oh, well, I'm just out the money. Too bad. Okay, but now let me ask, can we say that we've proven that the Earth is round? So let me turn off the sextant data. Turn on the protractor data, and I'm going to turn off the round Earth model, and I'm going to turn off the flat Earth model, and I'm going to turn on the round Earth model. Okay. In fact, let me zoom out. Let me turn on both models. Okay, and again, I keep moving the mouse without clicking it first. All right. So here is the flat Earth model. Here's the round Earth model. And so you guys told me a few minutes ago, you said it looks like the data fits the round Earth model pretty well. Let's turn on our error bars for the round Earth model, the round Earth data. Okay, here's the error bars for the round Earth data. Okay. Now I see a bunch of people talking, chatting, putting something in the chat box. Let me see if I can. When I share my data, the chat box goes away. I gotta bring it back. Oh, okay. Okay. All right. So I get a cool T-shirt with my membership. Okay. All right. Okay. So looking at this data, can we say with confidence that the Earth is round? Because the data seems to fit pretty well. Okay. Now, so this data looks pretty darn good. How about let's look at the sextant data. Wow, look at the sextant data. I'll even turn on the error bars, even though it's kind of useless because the error bars are so small. Look at that. Wow, they are right on the line there. Okay, so I'm going to relaunch our poll here. Now this time, the statement that I want you to tell me whether or not you agree with is, I'm going to claim that this data proves that the Earth is round. Now I'm going to wink while I say that because maybe it is, maybe it does, maybe it doesn't. I want you guys to tell me, based on what you see on the screen right now, can you say that we have proven that the Earth is round?
I accidentally.
Don't say anything yet. Wait until people.
I accidentally clicked the poll out, I think.
Oh, okay.
Because I can't find it.
Okay, don't worry about it. We'll just see what everybody else said. Okay, I still need 2 more people to respond. Okay, 1 more person now. I think one of you has fallen asleep here. Okay, hey Caleb, can you mute yourself, please? Okay, thanks. All right, so here are the results. Almost everybody said that you thought that this proves that the Earth is round. But one of you disagrees. And because these polls are anonymous, I don't know which one it was that disagreed. So the person who disagreed with the data, would you unmute yourself and tell us, why do you disagree with the statement that this proves that the Earth is round?
We haven't proved that the Earth is round. We've only proven that the Earth is not flat.
Tell us more. Tell us more about this. I mean, this data looks pretty darn convincing. Why are you not convinced?
We've only shown it over one section of the Earth. Perhaps just in Utah, we have this perfect curvature of the Earth, and that the Polaris is in fact 93 million miles away. But for the rest of the Earth, we don't know just from this data alone.
Okay, yeah, Polaris is actually 2,900 miles away, but I knew what you meant by that. But yeah, I completely agree with Luke. Let's zoom out here. We have only looked at a small portion of the data. Okay? We haven't looked at what happens up in the North Pole or in Alaska or in Canada or any of those. You never know. Something weird might happen. And in fact, let's go the other direction. We don't know what happens down here in Mexico or Nicaragua or Panama or Ecuador. So the fact that the data fits the model in this limited region, that might give us some degree of confidence that the Earth is round. But because we didn't measure anything out here or out there, you never know. It's entirely possible that if we go down to these lower regions, we might in fact find out that the Earth is not really flat. Okay. And guess what? That's exactly what does happen. If we were to continue, so we take our data here and we continue south. We don't stop in St. George. We keep on going. We go into Arizona. We go into Mexico. We keep on going. And what actually really truly does happen is that when we get down into Mexico and Honduras and Panama and Ecuador, we find out that the data, in fact, does deviate from the model. So Luke is exactly right. It turns out that the Earth really is not round. Okay. Anybody know what the Earth really does look like?
Isn't it an oval?
Yeah, say that again, Carrie.
It's an oval.
It's an oval, yes. The Earth is actually bulged out a little bit at the equator. And the way that we know that is because people have done this experiment that we just described. And we found out that, let me annotate here. And people found out that when you get further, okay, we'll try this one more time. Okay. People found out that when you get down further south here, the data really does deviate. And so it turns out that the Earth is not really a perfect sphere. What's really happening is that the Earth is actually bulged out a little bit at the equator. The distance from the center to the equator is slightly more than the distance to the pole. Now, on a percentage basis, it's pretty small. So if you were an astronaut out in outer space, you were looking at it, the Earth would look so close to being a perfect sphere that you wouldn't really be able to notice it. But if you measure it really, really carefully, you'll find out that the Earth is not a perfect sphere. Okay. So this is a really, really important concept that you guys need to understand. It is not possible to prove that any hypothesis is true. Any hypothesis at all. You cannot prove that it's true. The only thing you can do is you can prove it false. Okay? And in order to prove it false, you don't have to have a lot of data. Okay, so if you want to prove that the Earth is, if you want to prove that some hypothesis is false, okay, you don't need to have super accurate data, okay? Let me turn on the flat Earth model, okay? So here's the flat Earth model, here's the things. So even with a simple protractor, you can prove that the hypothesis is false, because we got one data point here that does not fit the mathematical model, okay? And that's all it takes. It only takes one data point. Now, it has to be repeatable. And other people who experiment, you know, if they repeat your experiment, they have to get the same results. But as long as we have one data point that doesn't fit the data, or that doesn't fit the model, that one data point is enough to prove that okay, hang on a sec. I'm getting some, okay.
Where's the headquarters of the Flat Earth Society? Because I would imagine it'd be Louisiana.
I'm not going to respond to that one. Somebody from Louisiana might get really mad at me. Okay, so all it takes is one data point, and that's enough to prove that the hypothesis is false. But, okay, let me clear this. Proving a hypothesis is true is another matter entirely. So those of you that claim that the round Earth model here, okay, so if we go to our sextant data, let's turn on our sextant data, turn off our protractor data, and let's turn on the error bars for our sextant data, okay? So Luke successfully argued that our data here doesn't contain anything north of Utah or south of Utah, and so he's completely correct in saying that. But there's also another argument that you guys need to know, okay? What if, let me temporarily stop sharing, okay? What if somebody were to invent a new sextant that's even better than this one? A sextant that can measure angles to, instead of 1/100th of a degree, it can measure angles to 1/1000th of a degree, okay? Let's see what would happen if that were the case. And let's go back and let's look at our data here. Right. So this equation where I've got the cursor right now, this is our error bar data. Okay, how about let's change it. So instead of plus or minus 1/100th of a degree, I'm going to put an extra 0 in there. Okay, all right. And so now let's look at a data point. Let's pick Moab here, and let's zoom in really close. Keep on zooming.
You're not
screen sharing.
Oh, I'm not screen sharing. Thank you. Okay. Let me fix that. Okay. All right. So this data point right here, this is Moab. So I'm zooming in on Moab, and I've got new error bars. My error bars are no longer plus or minus 1/100th of a degree. They're plus or minus 1/1000th of a degree. You see that the data point there is above the line, but it's still within my error bars, okay? Well, let's pick another one up here. Let's go to this data point up here. So let's go to price, okay? Let's zoom in on price. Hey, look at that, okay? Now these new error bars, remember, these are not plus or minus 1/100th anymore. These are plus or minus 1/1000th, okay? So you see that the model lies outside of the range of our data. Now, if I change back from 1/1000th back to 1/100th, okay, there we go. So with a sextant that I own right now, that's plus or minus 1/100th, the model lies within the range of error, okay? But if I have my nifty new high super high precision new sextant, which is plus or minus 1/1000th, you see there that the data, that the model passes outside of our area of uncertainty. And so you can see that even though we thought we had proven that the Earth was round, in fact, we can't. Right. So the important thing
You
that
have to
guys-
calculate for height of where you're taking the measurements, because
well, but not
sometimes
even that. Not even that. The idea that I want to drive home is that it is theoretically, fundamentally impossible to prove a hypothesis is true. The only thing that you can hope to do is prove it false. Okay. So if all of your data supports, if it all matches the mathematical model, then you can have high confidence that your hypothesis might be true, but you haven't proven it. Because as Luke said just a few minutes ago, prove is a very strong word. The criteria for proving something is very, very stringent. But we can prove something false, but we can't prove it true.
well,
Okay.
you can actually prove there's only one hypothesis you could prove, is that you cannot prove any hypothesis. Physicists
All right,
confuse screaming.
I'll go along with that.
Yeah.
Okay, well, that's pretty much everything that we're going to cover for tonight. Now, when you look on Canvas, let me go back here to Canvas. Am I sharing now? I think I'm sharing now. Okay. Yeah, so when you look on Canvas, you're going to see that there's a whole bunch of questions that basically just ask you to recreate what we have just done. All right, so question number 2 says basically just recreate this. So set Desmos a certain way. So click on this link here and then activate the flat Earth model, activate the round Earth model, set the window size as such, and then use Desmos to share the graph and then upload the graph. So basically, all I'm asking you to do on Canvas is just recreate what we just did. Okay, and I even give you the answers. And I'm just such an incredibly nice guy. Sometimes it scares me. So
Yeah. How many points is this worth?
10 points.
All right.
Okay. All right. So this should be pretty straightforward for tonight. Next week, we are going to start using the book again. Most of you have a book, but a few of you haven't yet gone in to pick up a book. So go ahead and do that, because next week we're going to start doing stuff out of the book. But it's stuff very similar to what we talked about, you know, precision and accuracy and graphing things and proving things, very, very similar there. Yep, that's the one. Yep. Okay, so do we have any questions before I end the meeting here?
So what about the question, like, did you say you would count my quiz as late?
I said that because you had a special reason, which we talked about later, or we talked about earlier, I will not count yours as being late.
Okay. And I'm assuming that as long as we did the text-based questions and we came up with something that's scientifically plausible, it counts?
Yes.
Okay.
Yeah. Anybody else have any questions?
Do you want us to text by in the text box before we go?
Yes, I definitely want you to text by in the text box. And also, if any of you have any questions that you're too embarrassed to ask, especially knowing that I'm recording everything, I'm going to end the recording right now, but I'm going to stay online so that if you want to ask some questions without having it be recorded, we can do that. So here, I'll end the recording.